Hello,
Hello,
how are you doing?
I'm good. How are you?
Oh, pretty good.
Can you hear me all right? I just want to make sure because I know last semester when I presented, I had some issues with that.
I hear a little static, uh, but it's not bad.
Okay, guess we'll have to work with that.
If if you really drop out completely, I'll tell you.
Sounds good. Thanks.
Hi, Tyler.
Hey,
I hope it was a little helpful yesterday. I know it was a bit rushed, and I appreciate your patience with that.
oh no, I was able to find my values to get some qualitative results, and I explained my difficulties.
Great. I mean, we have basically 3 weeks to get these things cleaned up. That's why we're doing it. That's why this semester I wanted to have everybody present early, so that we could all have some time to work together, to because they're all great projects. So I hope that we can cycle through a couple of times and revise it. I guess I sometimes joke that I should have gone to business school, gotten an MBA, because really when you run a research lab, you do more management than you do science. And with projects like this, my joke would be that I should have gone to architecture school, because if you do an architecture student, you do projects, and everything is about project presentations and repeated critiques, uh, which is not something we do so much in the science departments. I think engineering departments are more used to that, because they have more project courses where you build something and then you have to revise it and improve it. Something that I was talking about with we have a meeting. We have a meeting on Tuesdays with, and one of the people who is on that meeting is a professor in an undergraduate university in Pittsburgh, Carlo, and she works with a lot of undergraduates. And something that she encourages her students to do, which perhaps uh, we should, if we do this again, something to think about, is she encourages her students to present at undergraduate research conferences. Of course, depending on your project, it might or might not be appropriate for that. But I think over the past few years, there's certainly been many undergraduate projects that would have been nice to see presented. There's something called NCUR, National Conference for undergraduate research, that could be appropriate. There are also a lot of the professional societies have undergraduate presentation sections, which is not to say one can't present just generically if one has new research results as well. The one thing that makes this a little bit difficult is that there's a long lag. In other words, it's not practical for a student to. So her students, for example, the submission deadline for this NCUR conference was in December, and they're presenting now at the end of April. So there's typically a 3 to 4 month minimum lag between the time you'd submit your work and the time it would be accepted and presented. But I will, going forward, if people have work that they think would be worth presenting in that way, this class or otherwise, I encourage people to think about that. Could be research work you're doing for a professor or something else. But it's certainly, from the point of view of getting into a graduate school, from the point of view of getting a job, having presented in a conference is a plus. It gives you the opportunity to interact with people, connect. I try occasionally. I know you've probably gotten a little bit of spam from me over the past year or so, where else you'll get an announcement of a conference or a summer workshop or something like that. And so when I send those around, I don't do it without any thought. I'm usually thinking that they're things that might be of interest, at least potentially, to people. But it does take initiative on your parts to follow through, and especially because the lead times are long. Fellowship applications, conferences, all of these things. Conferences, typically the lead times are 4 to 6 months. Fellowships are often a year. So it's never too soon to think about your next project or your next presentation. And I do encourage people, whether it's something like this that you're doing for this class or something else, to put yourselves out there and do your best to be seen. The world is we're all competing for attention more than anything else in the world these days, I think. And projects like the ones you're doing here, or ones you might do for Paul's class, or if you're doing research with one of the faculty, with Vikram, with me, with Paul, these are ways of being seen. And we did have the experience in the past of students using their in-class projects for this class or for the fall one. They were entrees into good jobs or into graduate programs. And so I encourage you to, but you have to be fairly proactive about it. I know at least one person in the class is going to summer REU program, and those are good for undergrads. Good opportunity to meet people, make connections, and especially those summer research internships. Even if the result of the summer research internship is that you decide you hate whatever it is that they're covering, that's not so bad. At least you've learned something. And most of the summer REUs pay something. It's not as much fun if it's virtual as it would be in person. But the person I was talking to today at Pitt, at Carlo in Pittsburgh, University of Pittsburgh at Carnegie Mellon, a very good computational biology summer internship program. There are a number of those. Irvine has them elsewhere. And the deadlines are early. I think they're typically in January and February. So if you wait until March, April to try to find a summer program, it's too late for the best ones. There's always an opportunity of some kind, but it's not at the same level usually. It's a little more difficult. So thinking about that planning is important. Josh, do you know where Giuliano is?
He just texted me that he couldn't find the link to the class, but he should be joining me shortly. I just sent him the link.
Okay, so after some discussion with Josh and Giuliano and others, Giuliano is going to give us a quick introduction to how to do uploads to nanoHUB, and TJ could probably help us out on this too. I'd like to keep that short and probably have people do one-on-one consultation on that as needed. I was torn between how much time we'd spend per project and how much critiquing we'd do, and trying to get through everybody. After discussion with everyone, I think it's more important that we really try to get everybody's presentations done today. And then we have the opportunity to critique each other and come around for that. We'd have time for 2 more rounds next week and the following week. because I think it's critical that if these are going to be good applications, it's critical that we have the time to digest them and improve them. And so that means that you may have to try to keep your presentations and in-class comments a little bit short. And then we'll revisit these things twice and have the opportunity to dig into how to improve things more and more. And I think one of the most important things you could do in this class is to help your classmates do a better job on the projects. And last semester, some people gave up some excellent projects. And I think this semester, people have some great projects as well. And taking the time during the next few weeks to polish them and present them as effectively as possible, I think is really important. The other thing I have to remind you is that as normal, we are streaming this and recording it. You certainly have the right to not be streamed and recorded. So if you want me to turn off the streaming during your presentations, just say so and I'll do that. So Giuliano, are you ready to talk a little bit about how to?
Yep.
Okay.
How to set up your tools as.
How to set up an upload to nanoHUB. And again, I mentioned Giuliano is available for one-on-one consults for actually getting it done.
Yep.
And TJ knows how to do it too. So maybe just starting over just as a header since I've been chit-chatting. Welcome back everyone to lecture 12, which isn't really a lecture. Today we're going to have Giuliano talking about how to upload applications to nanoHUB using CompuCell. And then we're going to have our first round of student presentations of people's projects. So take it away, Giuliano.
Sure thing. Share screen here. So as James said, it's going to be a somewhat quick presentation on how to get your projects deployed as nanoHUB tools. Firstly, I'm sorry I'm a bit late. I couldn't find the link to join the Zoom, but I managed. Okay, so you should have received an email yesterday asking you all to have a nanoHUB account, which I think you have already, have a GitHub account, have Git Bash or something similar downloaded, and have it set up and whatnot. And also you're going to need your project files, which I think you have. And the final thing is you need to be able to open a command window and type Python and it work. So for instance, in Windows, if you press the window key and type in CMD, you can open up a command prompt. And in my case, kind of on purpose, my doesn't work. So it brings up the Microsoft Store trying to download Python. But that is fine, and there is a workaround, which is actually here, if you can guess how that works. But basically, we're going to type the whole path to the Python that comes with CompuCell to run that. So first, you should download the actual toolmaker, which is the script that will grab your project and generate the needed files. I'm gonna drop that link in the chat as soon as I can. Where is chat? Here it is. So you can try to do it as a go, or we can do it one-on-one later. But this is good practice. So in that link, you're gonna have a page similar to this one. And under the green button there, code, you can either clone it as GitHub, more on that later if you're unfamiliar, or download as a zip. For now, either of those options is fine, but later on we're gonna need to clone something. So if you want some practice, you can try to just do that on Git Bash, or if you are on Linux and have Git installed, it should just work. So second thing is we are gonna go to your GitHub page, homepage, and we are gonna create a new repository. Your homepage of GitHub should have this new here. And we are gonna give it a name. Class project or something more descriptive. Brief description, and then you need to set it to public. And these things are not that important, but you can already choose a license and add a README. And for license, anything that is open license should be okay. I'm not going to do that now. I don't need yet another repository on my account. But after you have your repository, now it's the time when we are going to need to actually clone something. So, for instance, here I have Git Bash. And I had already cloned the stuff that I'm showing yesterday as I was doing it. But what we want to do is clone the toolmaker repository. Here. This is the repository that we need to clone. And in order to clone it, we just do git clone and then the link that is here under code. So if I come back here to my Git Bash, so we can see what is in this folder and git clone this link. And now there is a new folder with the toolmaker. Okay, that's the first few steps. So now let's see what toolmaker actually needs. So if I go inside that folder now, I can see that there is a few files there, but the only important one is toolmaker.py. And as I said before, if I do Python, the script, it shouldn't work here because I don't have it set to path. But what I can do is from terminal, first I'm gonna navigate to this folder. If you are on Mac or Linux, this is gonna be easier. But navigating to that folder, which is nanoHUB, tools by TJ, blah blah blah. The nanoHUB there. And here. So now I'm in the folder with the script, and if I do Python and then toolmaker.py, which is the script. Oh, sorry. Yeah, the hard way. So in order to have Python actually work for me, I'm gonna, instead of just doing Python toolmaker, I have to type out the full path to the CompuCell installation of Python. And then I can do that. And that it loads the script appropriately. So without any arguments, it spits out a message telling you what it needs. So it needs a short tool name, which needs to be between 3 and 15 alphanumeric characters, no special characters, no spaces. And this is an important but not so important thing, but you need to remember that later because it's going to be part of the URL of your tool, and you're going to need to input that same exact name on nanoHUB when we get to that side of the story. So it needs a short tool name, whatever makes sense for your project. Then it needs the full path to the, all right, sorry, I missed something. So we made a new repository for ourselves back here, and that's where your nanoHUB tool is actually going to live online. So, give it a good name and whatnot. Then you need to clone that one to your local machine as well, as I did for the toolmaker. And again, it's git clone and the link of your repository, but not this link here, but the link under code. And so and that's one of the things that we need is the full path to that directory that it just cloned. And finally, the full path to the directory that has your project files. And by that, I mean the folder that contains the CC3D file and the simulation folder. So now, if too many things open. I come back here, and I have a bunch of nanoHUB tools living just up one from here. So if I do the same thing again, same command, Python toolmaker, and then, test. And in my case, since it's just a test, it's just for show, I'm gonna actually have it create a new folder. And it's gonna grab one of the tools that lives here. For instance, angiogenesis. Oh, right. That one should have worked. This is something different. Okay, so calling the Python script with Python toolmaker, gave it the name of test, telling to output it to this folder, which in your case is the repo that we just did and you just cloned, and the full path to this elongation demo that TJ made. And in your case, it won't have this message because you're already gonna have this folder, but since I don't, it's asking me if I want to create the folder. So yes, of course. And then that's created. And if I come here to nanoHUB and test folder, the elongation demo is there. So far, so good, I believe. Okay, so now you have all of the files that you need in your repo folder, but they are still not online. So now we need, so here are the steps that I just did, issuing the tool name and whatnot. So now we need to actually tell Git that we want to track those files and actually upload them. So if you go to git bash on that new repository that you had and type git status, it's gonna have a bunch of red text, which is the stuff that it's not being tracked and whatnot. So here I tested in a branch that is already all up to date, so it's not gonna have anything. But if I create a new file there, so that is here on this folder. If I just new text document and go back here, it's not this one. Ah, right, this is the new clone that I made. Now we can see the new text document there. In your case, you're going to have more files and folders. So we actually want to add everything to be tracked in this case. And now if we do git status again, it's going to have the same stuff as before, but now in green because it's being tracked. So let me just type in the important commands. Then in Git-like services, we actually have to tell the server why we are doing changes and why we are tracking stuff. So we actually need to give it a commit message, which we do by git commit m and then a string, which can, literally be just getting the tool started. And then what we want to do is git push to actually push it online. Now, if we go back to the repo that we created before on your web browser and do a F5 to refresh, you should see something similar to this. And your simulation files are going to be in middleware. Well, no, it's going to be in... Let me grab another example, which is better. So this is the one that I actually did yesterday. So we can see that it has 3 commits, just getting the tool started and then run permission, which you're going to get to later. And our files are going to be in main. So one interesting thing about... So we can see that your tools should be online. And one interesting thing about GitHub is that it allows it to see easily if a file is executable or not. So a few of the files that the toolmaker script made are in bin and middleware, and they actually need to be executable. So here it's a screenshot from this repository before I added the run permission, and we can see on the top left of the file, so if I go here, that in here, it doesn't says executable file like in here. And same is true for a file that is in middleware. So we actually need to allow those files to be executable. And that's easy enough to do. It's just this couple of commands. That one is gonna add run permission to the invoke file, which is in middleware. And this one, it's gonna add run permission to all shell script files that are in bin. And again, we need to give it a commit message and push it. So cool. That's all that we needed to do on our side of things. Now we need to go to nanoHUB. And here is the thing that I pointed out earlier about the short tool name, that you needed to remember that because we're going to need that right now. So go to nanoHUB tools, create. And if you're logged in, you're going to see. So you're going to be met with a page like this, which with a tool name that needs to match. The only important thing, everything else is fixable except the tool name. So the tool name needs to match what we gave it before. Then give it a title, the same title as our project probably. And I also recommend suffixing -CompuCell 3D to it so that it's easier. If people are just browsing for CompuCell 3D tools, it's going to make it easier to find them later on. Also a short description, which you give whatever you want. But yeah, just filling out of this. And then the next important thing is here telling nanoHUB where we are hosting our tool. In our case, it's a Git repository on GitHub. And then the next important thing is actually giving it the URL, which is the URL in the code menu. And finally, how nanoHUB should display our tools. In our case, the default of Rapture is what we want. Then to access, anybody should be able to run, etc., etc. And you're good to click on Register Tool. This process may hang for a bit, may take a few seconds to a few minutes. I recommend not refreshing the page or hitting back or anything after you click Register Tool, just hang in there and things should be okay. And after a few minutes to a day, you're gonna be able to see the actual status of your tool. So if I go back to my dashboard and go to my messages, I have here a message from the tool that I created yesterday, and you're gonna be met with a page which is similar to this one, or if the previous step of registering tool didn't hang, it's gonna put you here. The only difference is that you're gonna see a link saying my code is committed, working, and ready to be installed. And in our case, as we did the GitHub stuff beforehand, yours is. So feel free to click on that. And then you need to actually create a page to describe your tool. And here, description. Yours is going to be blank. I already have this filled up, so you have a space for your abstract. You can put in simple HTML in here if you want. Then everything else is really up to you. The only thing is powered by CompuCell 3D. And bio is something about you, I guess. Credits, citations. I don't think you have sponsors. Any references you have and any publications that come of this. And you can add other contributors if you did this as a group. You can upload supporting documents and screenshots. And you can add as many tags as you want. For this one, I added multiscale models, nanobio, bioinformatics, CC3D, and CompuCell 3D. So I do recommend you putting CC3D and CompuCell 3D. Just same thing if people are browsing nanoHUB and seeing CompuCell 3D tools. If they just search for CompuCell 3D and your tool doesn't have CompuCell 3D on the name or the tags, it's not going to be saved. And here a cool thing is that if I start to type, it actually suggests tags that match what I typed. And yeah, that should be it. And that was quick. But this is live streamed, so you should be able to watch back. And as James said, I'm available to help out in one-on-one sessions. And probably it's easier for you to be sharing the screen and me telling you what to do instead of the other way around. Yep, that's all that I had. James, back to you.
Okay, great. I know that that's not trivial to absorb, and so I hope that people are able to try it, and then when they get, if and when they get stuck, please go talk to Giuliano or PJ about walking through it. At least you've seen it, so it shouldn't be totally unfamiliar.
Yeah, I put my email in chat, and also I was quick, but I didn't want to take time from you guys' presentations.
Okay, so let's see who we've got. Gotta find the schedule. So we have Fonbo signed up first. Our order seems to be Fonbo, Jeffrey, Tyler, Collie, Devin, Drew. Is that okay?
Yep.
Okay, great. So Fonbo, why don't you take over?
I'll share the screen.
And people, please do take notes. And again, some notes from this and some notes from your review later. But really, we need to work together to try to make sure that everyone's project is as successful as possible.
Okay, so hello everyone. My name is Fanbo Sun, and my class project is trying to deploy and create a Jupyter widgets that runs the Mechanica, and we want to deploy it inside the nanoHUB. So I would like to say in advance that this project is not completely like a biological project. This is heavily based on a software project. But the objective and aim of this project is trying to help those people who want to run the biological and chemistry simulations that based on the Mechanica that can benefit from our project. So of course, the motivation comes from the fact that those students who want to run the simulation may not have any strong background in the computer science. So it would be hard to ask them to install like the Python version, the correct Python version, or the correct software distribution inside their computer. So it would be helpful if we can just build a binary form and, for example, to deploy it inside the nanoHUB, so they do not have to install anything and they can just run and they can just run their code inside the nanoHUB. So our objective is trying to design a GUI, a Jupyter GUI, that can allow the user to do like exactly the same thing that they do locally using the Mechanica. And also, if the user is not a terminal guy and he is like a Jupyter notebook fans, they can also use our like Jupyter widgets project to run locally on their machine instead of using the terminal. Okay, so in this section, I will briefly introduce what method and what tools we're going to use to build our project. The first, of course, is the Mechanica. The Mechanica is developed by Andy, and it is called Mechanica Real-Time Interactive Biological and Active Matter Simulation. So this Mechanica library is an interactive tool that can run the complex biological simulation and trying to solve these problems. And the Mechanica has two distinct features. One is, of course, the interactive, and the second is because it's wrapping with a Python API. So it's just very simple to use and to, so you can only write like a few lines of code to build your simulation. And then there's the Jupyter architecture, because we want to use a Jupyter notebook to build our interactive project. So inside this Jupyter notebook architecture, it basically has three different sections. The first is the user, is the client side, is the notebook cells that you can interact with. And the second is the server side, which is the Jupyter Notebook server, which takes the user interaction using the WebSockets and HTTP mechanical code, and can also run a simulation from that. And the connection between that is using the CeloMQ. The second is the widget. So why we want to use a widget, because the widget is a very simple tools that can display like an interactive GUI for the user to play with. And it also has a great features because it can synchronize very well by using the widgets. And these features can be described inside this architecture, because the widgets architecture uses the COMM package. So instead of the traditional Jupyter architecture, the kernel and the client side, they talk directly through the COMM package. So there's no external request to send requests to the Jupyter server. So the synchronizes very well using the widgets. And the other thing we want to apply to listen to the keyboard and mouse event is called the event widget. And this widget is created and using by an existing library called IPL events. And this event widget is just like other traditional widgets, for example, the image label, and can also interact with that. So this is a small widget that displays. So if you click on the label, you can see the type is click. And if you enter the mouse or press the key, it will give you different types. So this thing can correctly see what mouse or what keyboard event you are right now using, like inside the Jupyter server. And then it's about how we implement this project. The first is our planning. Our initial planning is very simple. It's just we have a widget here, and we use the mechanical code to send back our image and display the image inside the widget. Also, we will have the mouse and keyboard event to interact with the image to like move and rotate the image. And then there's our overall architecture of this project is can be seen in this graph, and basically it also divided into three parts. Although this Jupyter part is not usable. So for the client side, the user have to put their code here in order to create their mechanical object there. And also we have multiple widgets function here. For example, the start, pause, and reset can run the simulation, pause simulation, and three different mouse event and keyboard events that can rotate and zoom in the image. And these things are done inside the IPython kernel by using the widgets and threadings. Typically, we're using three different widgets to implement this project. The first is image, button, and the event widget. In threading, we're using a background thread, which is the very important things we have to use, and also a main thread. And this is the logic flow that runs our project. You can see here the background thread continues running when you initialize the mechanical object. and it keeps updating the image, so it always gives you the newest version of image. And here we have a global value called flag. So if so this flag controls the running state of the simulation. So if the button, if you hit the button run, it will set the global flag to be true. So the simulation can step up into the next step. So it's running simulation. And another thing is for the mouse event, because we want the user to click the mouse and hold the mouse in order to move the object. So we will also set a flag called the mouse flag, which only set to be true when the user clicks the mouse. So here is the demo of the widget function we implement. So this is the mouse rotate. So if the user click and hold the mouse and do the mouse move, you can see it moves the screens and it rotates the angle of the camera. And this mouse shift is, this thing is done when the user hold the shift and also hold the mouse and move the mouse. It will shift the screen of the camera. So next, the next is the mouse zoom function, where you hold the mouse wheel and rolling up and rolling down will just adjust the angle of the camera. And another is the keyboard reset. So if you are in a different angle, you hit the R button in your keyboard, it will just reset the camera. Okay, and then it's the run start reset function. So if you hit run, the simulation will run, and also in the meanwhile, you can also use the mouse to rotate the screen. And when you hit the pause, the simulation will pause. And if you hit run again, the simulation will begin to run. And if you hit reset, it will reset all the things inside the box. But you can also re-initialize all the things by re-enter your code. So it will recreate all the things into the initial state. And then you hit run and pause, it will do the same things. Yeah, and then this section is introducing how we package and deploy it inside the nanoHUB. So the idea of packaging is trying to package this Jupyter code into a black box, so the user do not have to know anything about the Jupyter notebook. They can only copy their code that runs locally in their machine to the Jupyter notebook. That the Jupyter notebook will automatically detect if the user used the Jupyter notebook to run the simulation or they are running it in the terminal. So this is demo of running locally in the terminal or in the Jupyter notebook. So if I'm running it in terminal by calling the Python and like bounded as the lattice file, because it runs locally in the inside the terminal. And then I'm copying exactly the same code that I runs in this file. And I'm entering the locally inside my Jupyter notebook and I'm paste this exactly the same code and I'm running it. It will automatically detect you are running in the Jupyter notebook and trying to give you an image widget that runs that. And it has all the functions and you can play interactively with the image. And this is trying to deploy in the nanoHUB. So when you go to the nanoHUB, And inside the Jupyter Notebook GPUs, it's just waiting for me. Yeah, so here you open new Jupyter file inside it, and reset all things, and just do the same thing and try to initialize the empty widget and try to add things in it. You can see it does the same thing as running locally inside the local Jupyter Notebook. It can also run. It can also run pause. But you have to notice here that the performance of this is kind of slower than what we done inside locally. These are the questions we have to solve like in the following weeks. So it can be seen that there is an apparent lag when you like trying to run all the things in the nanoHUB, because the possible reason for this is the first is the rendering time in the nanoHUB. The rendering time is more than running locally, so the time you're generating a new image is higher than you running inside inside Jupyter Notebook inside like running locally. And the other thing is the events are essentially queued inside the kernel, and are processing very slowly inside the nanoHUB than you're running it locally. Because you have a background thread running forever. So if you have many events that queued inside the nanoHUB kernel, it will just essentially delay like what you command and what you interact with the image. And for how to solve that, I create several tasks for solving that. First is about the running time. The running time. So we have a feature called the performance counter, which can tell us how much rendering time we have when we generate an image. And I will test 3 cases. One is on the nanoHUB, and one is running locally in my Jupyter Notebook, and one is locally with the terminal, and to judge if this running time matters a lot in our project. And the second is about the queue time. And the queue time is kind of a trade-off between the delay time T and also the advance E. So the delay time is the delay time inside our background thread. So if the delay time is 0, that means the background thread runs very fast. So it will generate the maximum number of the events that they have. So it will have a huge queue time. But when you increase the delay time to be 1 second, of course we will have fewer events, but then we will have a huge delay time so the image will update like 1 second per image. So it will also hurt our performance. So my task is try to select a decent time from 0 to 1 that can be like that the user can run, that can give the user reasonable experiments when they are trying to use it in the nanoHUB. So this is the future task is first is to solve this delay issues. The second is kind of about adding the clipping pens, which is also a function that we may employ inside our Jupyter Notebook widgets. Yeah, I think that's all for my presentation.
That's great. I was just wondering, you have this running, this should work since Isn't Colab also a Jupyter Notebook interface?
Yeah, this is also in the nanoHUB Jupyter Notebook.
But I was just wondering, I mean, so if you have this deployment working, it should also work on Colab?
Yes.
Yes.
That would be great. Have you tried it on Colab yet?
We have not tried it on Colab. Really the only issue, and it's really minor, in that right now the binaries are built for the nanoHUB version of Linux. To make, there's this thing called many Linux binaries, and basically you compile your code in Docker, and I just haven't had time to figure out how to build a Docker script to compile it that way too.
No worries. I just wondered if you could see if the latency issues were better on Colab than on Jupyter and then on nanoHUB. That might be worthwhile because long term, probably Colab will be around longer than nanoHUB. Although it doesn't give you the publication and findability, I guess that it's the Git repository is findable, but not the nanoHUB, not the Colab itself, the Colab deployment itself. If I understood right. But I think that's fine. Other questions? Any comments, questions from the rest of the class?
I do have a question. Is there any way for users to access other types of widgets that are not just image widgets?
So right now we only have a interactive image widgets with like three button widgets here. But you can essentially add like your custom widgets inside the Jupyter Notebook.
So any IPy widget should work, in other words, or at least anyone that nanoHUB supports.
Mm-hmm.
Is that?
Yeah. But I think you have to embed it with our image widget, or
Okay.
it will not work. Yeah.
Okay, cool. Yeah, that was my question.
Other comments or questions? That's very nice. I'm eager to see this happen. I think it'll be pretty neat when it gets out there. All right. Thank you.
Yeah,
I guess that was great. Thank you for leading off. I guess, Jeffrey, you're next.
Okay. One second. I have to quit and reopen Zoom to share my desktop because it wasn't.
That's fine.
I haven't
Whatever
done that
you
on
need.
this
No
computer.
worries. While he's doing that, I noticed if you search deploying Colab applications as static applications, there are a bunch of secondary tools. There's something called Anvil. It looks like it's a wrapper for there. Please go ahead, Jeffrey. Thank you.
Okay. So here's the outline. I'll talk about the concept and physics of fluids and how they're usually modeled, and then get into dissipative particle dynamics, which is a different way and what is used in Mechanica, and then go over results. So here's the goal of this was to use Mechanica to simulate fluid flow, and we started out with some simpler ones just to kind of test the Mechanica's how it would simulate things, and then build up and add chemical reactions to generate the fluid flow, because that is the what they did in the paper down here, and use this fluid flow to generate structures, which can be used for things like microfluidics and chemical sensors, among other things. So to start out with the physics, this is what is usually modeled. The Navier-Stokes equation. You have the continuity equation. This isn't what is used in dissipative particle dynamics really, but for completeness, it's here. You can see the different parts. Some of them are maybe similar. We've talked about like pressure gradients and the diffusion in class. And so what you do when you're typically modeling, you break the differential equation to simpler algebraic or difference equations, and you numerically integrate them. You can see here what this looks like. The time and space parameters are discrete, like similar to CompuCell, and you can do this in what's called an on or off lattice approach. The stuff like in CompuCell is on lattice, I think, where space and time are both discrete, and things move more deterministically, I guess. Or you can use something like dissipative particle dynamics, where the time is discrete, but space is more continuous, and there's an element of stochasticity, which we'll see in a second. And also when you're simulating, I guess in all simulations you have boundary conditions, but some of the ones that will be used in the code I have are periodic and reset, which is also periodic, but it's used in the chemical simulations, where when the particles reach the boundary, the chemical is reset. So it's not like the particle itself is behaving periodically, but the chemical isn't. So it is, when it comes back around, it's back to no chemical content in it. And something pretty common in fluid dynamics is the no-slip boundary condition, which occurs in viscous fluids because the adhesive forces between the boundary and the fluid are stronger than the forces between the cohesive forces between the fluid and itself. So at the boundaries, the fluid tends to move with zero velocity relative to the boundary. And some issues that you'll see in the exercises I have concern these boundary conditions, and how when there's no potential added at the boundary, then you we'll see higher pressure there. And I made this animation so you can see what happens when there's no potential. It just moves and bounces back. And when you add the potential, it depends more on the velocity. So it will do the same thing as if there's no potential when it's moving quickly. But otherwise, if it's moving slower, it'll kind of that. In dissipative particle dynamics, rather than individual good particle size, you have you consider the particles to be packed molecules. And as I said, the time is discrete, but space is continuous, and the governing equations are here. It's still Newton's law, but you have a conservative force, a dissipative force, and a random force, and they act on technically all the particles except itself, but we'll see later that there's a cutoff radius. So they only interact within a certain distance of each other. The conservative force is just a standard force due to a potential. And the dissipative force acts to align particles along a trajectory as they approach each other. Well, the random is kind of the opposite of that. And these two dissipative and random forces, they act as a thermostat. And it's been shown that there are certain conditions that need to be met in order for the simulation to be physically reasonable and make sense from a thermodynamic perspective. So this is what the conservative, dissipative, and random force look like when you want to write it out. You see, here's the cutoff radius in all of the simulations I have. It's equal to 1. So, like I said earlier, technically these all interact with each other, but once if they're outside of the cutoff radius, then this will be 0, and all of them will be actually, because this W here is the same thing. So in the simulations, you have these the parameter A, gamma, and sigma, which you'll use to adjust the strengths of these forces. And there you'll be able to see how you can test whether when this holds here, whether you'll eventually reach a state of equilibrium or not. And then, yeah, the random variable is what makes the random force random. The wave functions, you can see since outside of the cutoff radius, they are 0. They basically, if the particles are closer, then the forces will have more of an impact. And if they're farther away, it'll be less. So yeah, there is some chemical stuff, but I didn't include it right now because we kind of just talked about it in class, I guess. And I'm also wanted to save a little bit of time because it's, well, I guess I'll play this. Difficult or not, as I wanted to show how to run some of the code real quick. So I'm still not able to use this on my Mac. So when you want to, I tried to, and also I can't either right now. So I'm sorry that it's kind of just the plain code right now. But I commented a lot of things, and you can see this. And when you want to run a simulation, you have to just go into your terminal and type, just type Python in the sorry, I'm not used to Windows. Yeah, and then it'll pop up and the plots will appear. So yeah, I'm explicit in the exercise questions so you know where things are and how to do that. But yeah, I think that's all I have now.
Comments, questions? I mean, you could certainly walk through any standard. Now that you have that, you could walk through a standard fluid dynamics textbook and basically animate all of the different. You did flow, you did Poisson flow, you did a few examples already. I think it'd probably be pretty straightforward to do some more of those. You were working on visualization, I know.
Mm-hmm.
One thing that's not so simple with these particle methods is seeing what the flow patterns really are. Of course, that's a lot of extra work. I'm not saying you have to do that. But what would you like to do to finish this up in the next few weeks? What are the pieces you'd like to put together to finish?
I mean, I have the particle, the fluid flow pushing and moving the particle, which was the what I was working towards. I can probably add more of the stationary particles to see if they build some kind of 3D kind of tower like in the image. But also, yeah, I need to get, right now this code just has the old plots, not the time averaged plots, because I wasn't sure. I can't run it, so I don't want to send people stuff that's not going to work. So I'm still writing that, but hopefully in a day or two, I'll have the nanoHUB dev account and be able to execute it.
Great.
Yeah, what we were thinking about for the nanoHUB app is where you have a single notebook, and that introduces the basic concepts where you start off with a simple model, then go to a driven Poisson flow one, and then show these are the terms we need to add. Then add the driven one, show these are the terms we have to add. Then a more sophisticated one where now we want to add chemical substrates to objects and diffusion between them. So we add these, and then finally building up where you have adding a chemical dependent force between objects, and then so basically they pentagon that rather sophisticated model that Jeffrey's doing out of his paper.
That sounds great. That's what I was saying. I mean, you could basically take a fluid dynamics textbook, turn it into, retype it into Jupyter notebooks, and then have each of the diagrams or exercises in the notebook be a simulation, a fluid simulation using Mechanica. So I think it's extremely flexible. Once you've got it working, the one thing you need to be able to do is visualize the streamlines somehow so that you could get a sense of what those are, or at least the velocity. So you have that mean velocity versus position for the Poisson flow. So I think that's very impressive.
Yeah, I have plots for all of the other ones as well, but I didn't add them. I have a plotting class and I'm just copying some of the plots into the code. So,
well, I bet you don't have to show everything today. I wasn't saying you have to show everything. I think that's great. I know with losing your computer didn't make your life easier.
yeah, it's I finally got NumPy working yesterday, so making progress.
Does anybody else have any comments, or shall we move on? I think, as I say, we have time. These are recorded, so we could go back, and if you want to watch them and make comments offline, that's okay too. I have Tyler down as our next speaker. Thank you, Jeffrey. That was great. Tyler, you ready? You're muted, Tyler.
I just realized that.
I guess you should probably go back to the first slide and start over. So we have it.
Good idea. Okay, so the goal of my project was to replicate the results of an inspiring paper about the early immune response involving CD8 T cell differentiation. And a little background into my project is a little about the immune response. So CD8 T cells play a crucial role in fighting off infections. They can either signal for different cell types to come into play or directly kill pathogen infected cells. And I use viral infection for an example. The immune response includes the presence of interferon to slow the infection, while the immune system differentiates and builds cytotoxic T cells in order to control and overcome the infection. And typically in an infection, there will be some memory T cells that hang around afterward. Those are T cells that manage to survive the end of the infection. But about my model is it mostly describes the early immune response. So it's going to aim between under a scope of about 5 days. And it's going to focus on the production differentiation of T cells, going over about 4 or 5 differentiation states. And about the model specifically, there's 5 cell types. There's naive, which will differentiate to pre-activated, then to activated, then to effector. And this is mediated by contact with APC. And the diffusion field that drives this differentiation as well is interleukin-2, IL-2. And from here, APC will uptake antigen from the environment and work their way back to the lymph nodes about 2 or 3 days. And from here, they come into contact with naive cells. And from here, the naive cell will become pre-activated. And once pre-activated, IL-2 begins to be secreted, as well as IL-2 receptor that begins to be produced. And once the level of IL-2 is sufficient, the receptor will become active and will cause the cell to become active. And then additionally, pre-activation stimulates the production of TBET. And TBET is a protein that once its threshold is reached, will allow activated cells to become effector cells. And these thresholds and this IL-2 field are controlled by an intracellular ODE model. And to start, the simulation has 3 APCs, 30 naive cells on a 200 by 200 domain. And as I mentioned before, once a naive cell comes into contact with APC, the IL-2 becomes present. And here is a conceptual model of my model. Up here, we see just the simple linear pathway that I mentioned. Naive cells will come into contact with APC and become pre-activated. And then once IL-2 receptor, this IL-2R star, once this level is reached, they will become activated. And from here, TBET will cause them to become effector cells. And through FOS-FOSL interaction, this can increase the rate of apoptosis by increasing the production of caspase. And that can be better described in this arrow diagram, where naive cells becoming pre-activated is mediated by APC contact, and pre-activated cells are subject to apoptosis by caspase mediated apoptosis. And in my model specifically, the parameters work out so that when a pre-activated cell detaches from APC, either by the APC dying or drifting away, caspase levels will rise and apoptosis will happen quicker. Additionally, pre-activated cells will move to activated once level of IL-2 is sufficient. And like pre-activated cells, activated cells are also subject to apoptosis. And here, activated to effector is mediated by TBET. And also, effector and activated, if they come into contact with each other, this will increase the FOS-FOSL interaction, which will catalyze caspase production as well, and increase apoptosis rate for those 2 cell types. And here's a look at the ODE model. Some key parameter values here. This F of APC term, it describes the amount of APCs an individual cell is in contact with. So this number can vary between 0 and 3. IL-2CM is the amount of IL-2 at the surface of an individual cell, and this parameter is used here, and it is a key factor in the amount of activated IL-2 receptor. TBCM is the sum of TBET concentration from all neighboring cells that are in contact with one another. And this only plays a role in the non-activated and activated FOS equations here, which are only used in the caspase equation to increase or decrease apoptosis rate. Here we see TBET is a term that will always rise throughout the simulation and never really saturates. And this, as we'll see later, is kind of giving me some issues. It's kind of throwing my simulation off, but I'll describe that later. Here, this is a simplified version of my model just to visually see the expected results. So these are the result of the ODE models being implemented into a single cell, where the parameter F of APC was changed manually. And here we see, here's the expected results curve here. This TBET curve, as well as this IR star and caspase, all of these behave properly in the simplified model. How do I go back? Here. Sorry about that. So we see that the shape of these curves are as expected in the paper. And for some reason, when I moved into my more complex model, that was giving me some problems. So here we see the simulation as it is. I have adjusted the thresholds since I mentioned that they gave me problems with the values. The thresholds are adjusted so that the cells differentiate according to their proper timescale. So here we see naive cells coming in contact and becoming green pre-activated. And once their threshold is reached, they will become activated, which are these orange cells, and eventually becoming effector cells that you see purple. And the implementation of caspase also, it reaches its correct steady state value. However, it reaches it much quicker than it should be. Therefore, I added a time constraint to it so that it only became active when, or the value, excuse me, was only used after a certain time point. So that was to prevent all of my cells from dying too soon. Yeah, so here, this is the expected outcome of the simulation, which qualitatively is the same or very similar to that just seen previously. And the proliferation of cells also works correctly, occurring about every 8 hours or 480 Monte Carlo steps in CompuCell. And furthermore, we determined that there was likely an error in the paper concerning the parameter values for the ODEs, or possibly a term that was used incorrectly. Or it could have been an implementation of my code that I need to take a look at more. But here we see the different cell counts. We see naive cells over time decreasing as the number of pre-activated and activated cells increase. And then we see this rapid rise of effector cells and decrease of activated cells. This is due to the proliferation of cells, this upward yellow part. And here is where that the proper time at which activated cells should become effector cells. And that's why we see this crossing over here. And as I mentioned, my caspase threshold value was modified and coupled with a time condition so that it would occur properly. Otherwise, my cells would have died too soon, or it would have, the cell population would grow out of control and be way more than it needed to be. And yeah, moving forward with this, I need to fix the ODE behavior so that my threshold values are a bit more correct. And additionally, I'd like to add a steering panel feature so that I can change the starting amount of naive cells, so I could simulate a condition such as immunodeficiency, and possibly even the addition of a drug to boost the immune system, if that would be possible. And yeah, that's pretty much where I'm at right now.
Okay, comments, questions? We'll need to maybe have your classmates put their eyes on your code if we get the code so people can run it, and see if we could find why that single cell model seems to reproduce the simulation results in the paper and not the multicellular version of it with the same code.
Yeah.
I think it's an intriguing model. I think trying to think about what one could do to explore with it. Your comment about immunodeficiency and potentially immune stimulation, I think, are interesting. There was an interesting comment in the talk last week that was given in our IMAG working group on modeling infections by James Moore at Imperial College London, that when you get vaccinated, vaccines have adjuvants, alum being the most classic one. And these are not the active component of the vaccine. These are add-ins to the vaccine, and they make the vaccines much, much more effective. And the theory of the way adjuvants work is that essentially they're irritants that excite the innate immune response. The vaccine, of course, is exciting the adaptive immune response because you want to produce antibodies and CD8 plus T cells. But apparently your lymph nodes do a much better job at recognizing the antigens that are presented to them by the disease or the vaccine if they've first been stimulated by the innate immune response. And so the adjuvant essentially is inducing inflammation or almost an allergic reaction in your tissue, causing the swelling that you get after the injection. And that signal then tells the immune system, lymph nodes in particular, to be ready for a signal that they have to respond to. And so the idea of doing some kind of pre-stimulation to prepare the immune response for the antigen presenting cells, I think is pretty reasonable. So I think that could be really interesting. So that's great, I think. And I understand it's frustrating to try and track things down when there's a problem. We'll keep working on that. Anybody else have comments or questions? No. I guess people are taking our statement that we want to get through the whole list of people to heart. So, okay, that's okay, but you're not off the hook. Remember, you're not off the hook making comments in writing, even if you don't ask questions here. So, okay, great. Thank you. Kali, I think you're next.
All right, let me get this pulled up. All right, so as you all have probably figured out by now, my project this semester is about developing a multicellular model of the fruiting body development for the amoeba, Dictyostelium, Discoideum. So first, the biological background. So D. Discoideum is a soil-dwelling amoeba. It is also known as a slime mold, and it is referred to as a slime mold because these amoebae can aggregate together, forming, well, the slime mold. That's the element that gives it this name. The life cycle of this amoeba starts with the individual amoebae sending out cyclic AMP signal. Cyclic AMP is a biological signaling molecule under starvation conditions. This causes the aggregation of the amoebae, forming a motile slug. The slug can then move to a suitable environment, and the cells of the slug differentiate into pre-stalk and pre-spore cells. So that's like here in the diagram. That leads to the growth of a fruiting body consisting of a bulb at the end of a stalk. And then the bulb at the end the spore at the end then releases spores, which then become new amoebae, starting the cycle over again. So you can look at this diagram here to see that cycle. Factors influencing the developing of the fruiting body include chemotaxis towards the cyclic AMP signal, ammonia inhibition of that cyclic AMP signal, and thermotaxis and phototaxis, which I did not cover in my project, but those are factors found in literature as well. And why do we care about modeling slime mold? Well, it's an important model organism in biology because of the fruiting body formation and the aggregation into the motile slug. It is used to study things like chemotaxis, motility, cell signaling and cell differentiation. And here's a picture below about that shows you what it looks like. I had 2 paper sources for this project. The first is the base paper is a 2001 paper on how amoeboids self-organize into a fruiting body. This paper is where I got the qualitative results that I'm trying to replicate, the different cell types involved in the model, the contact energies between those cells, the target volumes of the cells, and the ammonia inhibition of the cyclic AMP model. The second paper from 1999, Migration and Thermotaxis of Didascoideum slugs, a model study, is where I got the ODE model for cyclic AMP concentrations and cell refractoriness. Project challenges, I know that we had to discuss these in the presentation. So some of the papers that I used had some vague explanations for the model. So the cyclic AMP model was not explained in the 2001 paper. That's why I had to go to the 1999 paper. Yeah, I have a meme. I try to be funny. Yeah, so that's why I had to use 2 papers for this project. Additionally, in that model, it was unclear whether I was supposed to use the amount or concentration of cyclic AMP in ammonia. And I ended up going with the amount in the end because that's what we thought the wording implied. The cell differentiation trigger was a little unclear. So according to the model, cell differentiation, the probability is dependent on the contact area of that cell with the cells that it's trying to differentiate into. So it was a little ambiguous whether there was like a threshold for that would then trigger differentiation, or whether it was based on a 0 to 1 probability distribution. I ended up going with the second one. And then the initialization diagram from the qualitative results I'm trying to replicate, the resolution was a little unclear. So sometimes it was hard to tell where certain cells were located, but I did my best with that, and I actually think that probably wasn't terrible. So yeah, sometimes when people say the model is replicable, it may be more difficult than it seems. Okay, so now going into the biological model, this model involves 5 different cell types. We have pre-spore cells, which will turn into the spores, 2 types of pre-stalk cells, which will then turn into the stalk, the actual stalk cells, and then pathfinder cells, which are supposed to guide the stalk cells down so that it can root in the soil. There are also 2 extracellular components in this model, the slime sheath and the stalk tube. So the slime sheath is like they're just both materials that exist outside the cell that we can treat as like one giant cell, if that makes sense, in CompuCell 3D. And then we have 2 media, air and soil. So here's the initial condition diagram, which I said had a little weird resolution to it. So here are the pre-spore cells at the bottom, pre-stalk O cells in red, pre-stalk A cells at the top. Underneath that is the stalk cells, and then underneath those, it's kind of hard to see, but they're in purple, are the pathfinder cells. And then the slime sheath is located throughout in yellow. So now going into further into the biological model, pre-stalk O cells will differentiate into pre-stalk A cells, which will in turn differentiate into the stalk cells. So there's this kind of chain going on to develop the stalk in the fruiting body. The pathfinder cells, as I said before, will guide the downward elongation of the stalk. The tube cells will eventually surround the stalk, think like protection, and then the slime sheath will surround the bulb at the top. Now kind of going into kind of where the biology and the math meet, pre-stalk A cells will generate the cyclic AMP signal. This will be an oscillatory signal, so the cyclic AMP levels will rise and fall. This signal is then relayed by pre-stalk O and pre-spore cells, and then ammonia present will inhibit the amount of cyclic AMP that can be relayed. So here's a little, and ammonia does this in the model mathematically by impacting the cell excitability. So that will impact whether the relay will fire. Here's a diagram of cyclic AMP, just so you can put a compound to the name. Now going into the mathematics. So this table is from the 2001 paper by Murray et al. It shows every single cell type, cell and extracellular material, its contact energy with the other media and cells and extracellular materials, the approximate number of cells that we're aiming for, the target volume for each of the cells, and its behavior with regards to cyclic AMP. So these variables served as the basis for a lot of my XML file, and then my initialization. Going into the ODE model, these two ODEs were taken from the 1999 paper, adjusted slightly, showing the change in cyclic AMP-C over time and the cell refractoriness R over time. And then here, K is a constant. Oop, the paper didn't really explain what it was, unless I missed it. So F of C and epsilon of C in these ODEs are themselves piecewise functions. So the value of those functions will change depending on what the cyclic AMP concentration is. So as you can see here, I won't read all this out. And all of these values here, big C1, little C1, C2, C2, C3, C3, and then epsilons 1, 2, and 3, these are all constants. The implementation, as you probably remember, I ended up doing this in antimony and in CompuSolid 3D. Here's that implementation. We account for the ammonia concentration in this model by involving the ammonia concentration in this, what's written in the paper as alpha of tau n, but here is a underscore tn. That is the adjusted cell excitability that takes into account ammonia concentration. So if there is more ammonia, that cell excitability will go down. Or well, yeah, it depends on also what the A of T value is up here. So an oscillatory cell will have a negative excitability, and then a relay cell will have, depending on the model, in the initial 1999 paper it was positive, but in the 2001 paper it could also be negative. But the two excitability values lead to the oscillatory and relay behaviors. So now let's go into look at some results. So here is, on top is my initialization at time step 0 of what we're trying to see in the paper. So if we go back a bit, this is what I'm trying to emulate here. So here's at time step 0, we have all the cells initialized and we have that slime sheath present throughout in the light blue. And then after a while, once we reach time step 60, we'll see that slime sheath migrate to the outside, just as we'd like to see here. As you can see at the 2-minute mark in the simulation, we see all the yellow that was previously distributed in the inside here, now on the outside. Something else to observe here are the pathfinder cells. So the pathfinder cells at time step 0 are the purple cells underneath the yellow cells. At time step 60, we see them surround the stalk cells, which is also what we see here in the 2-minute diagram from the paper. So these are both expected behaviors generally. The problem comes in when we try to do cell differentiation. So there are a few things going on here. What we're seeing here are the red pre-stalk A cells are differentiating into stalk cells, and then the pre-stalk O cells in green are also differentiating into pre-stalk A cells, but it's not following the nice organized pattern that we expect from the paper. In the paper, we want to have a downward elongation of the stalk cells going to the soil, and then we'll see the upward growth of the fruiting body. This here, what we're seeing in the middle, is not that. So I have a few ideas for this. It could be that the pathfinder cells aren't chemotaxing quickly enough to elongate those stalk cells, and then therefore decrease the contact area that those stalk cells would have with the pre-stalk A cells. It could be that the cell differentiation function that I'm currently using, the probability-based one I'm using, maybe isn't the best to use in this case. So what I'm currently doing is calculating the fractional contact area of a cell with the cell type that it is supposed to differentiate into, generating a random number between 1 and 0. And if my random number is less than that contact area, that fractional contact area that I calculated, then the cell will differentiate. maybe this is too deterministic of a method. Maybe the cell differentiation, I mean, it probably has to be mitigated a bit more. Maybe in order to get some results, I need to delay cell differentiation entirely for a certain amount of time so we can decrease that contact area between the stalk and pre-stalk cells, so we don't end up with this diagram here. So in order to further examine how my suspicion that chemotaxis of the pathfinder cells would have something to do with this, I ended up looking at the the cyclic AMP profile of the simulation. So we have high levels of cyclic AMP here among the pre-spore and pre-stalk O cells, lower cyclic AMP levels in the stalk cells, which is like we expect that. So we should be seeing the chemotaxis of the pathfinder cells go down, which will then pull the stalk cells with it, etc. So it could just be that maybe I'm not running the simulation for long enough in order to see that effect. That could very well be it. Maybe some way that I need to increase the speed so this happens in a reasonable time for someone trying this on nanoHUB. So for next week, I need to play around with some of those ideas. Potential exercises that I'm thinking about for the nanoHUB, the written portion of the nanoHUB app. I think two obvious ones are to adjust the contact rates for the slime sheath and observe changes in migration to the outer boundary. I think that's something very easy to observe because it happens rather quickly in the simulation. What I showed you previously was time step 0 to time step 60. And even before then, like time step 40, most of the slime sheath was already at the outside. So this seems like something very observable for people to check out. Also, once I developed a proper method for the cell differentiation, it would be interesting to adjust those probabilities or change just to see how the different cell types how the development of the different cell types over time will play out. I'm not sure for exercises if it would be appropriate to touch the cyclic AMP model. Maybe that could be a possibility. But for the line of thinking I had was to play with the cell types in the development more so, but I'd be happy to take feedback on that. So future work, as you saw, cell differentiation, chemotaxis, and also see what happens if I run this simulation for significantly longer than I have been. Right now, in the paper that I used, they're using like each simulation step is like 0.1 seconds. And if you saw from previously in the presentation, I had shown like at the 2-minute mark, that is 1,200 time steps. Not sure I should maybe play around with the time steps for the sake of the nanoHUB app to get things to move more quickly. So that's where things are going to be headed for the next couple of weeks.
Great. Comments, questions? I remember Stan had a lot of trouble getting the mechanics to work. He had to fiddle with those cell properties a lot to actually get the stalk to go down.
Yeah.
And he shows in his thesis a bunch of cases where it fails.
Yeah.
Where it squiggles to the side or doesn't do the thing that he wants. And so I know there's some fine tuning involved in getting that to work. So I'm happy to sit down with you later in the week and try to work.
Expect an email soon.
That's great. Okay, other comments, questions? No. Okay, Devin, I think you're next.
All right, one sec. All right. Hi, everyone. My name is Devin Keller, and my project focuses on a cancer's microenvironment and its effect on somatic evolution for that tumor. So I'll start by going over a little bit of background that's relevant to my model. There are a few characteristics of a tumor that causes somatic evolution to occur. The first is selection pressures from the microenvironment. A tumor's growth can be dependent on nutrients, such as glucose, for example, oxygen, host immune response, and other factors. And these are considered hallmarks of the progression of tumors. Another factor of tumors that we have to consider is the heterogeneity of them, meaning the cells making up a tumor can be very different within. So this makes it harder to eradicate the whole tumor during treatment. And then lastly, this model looks at how the concentrations of adhesion molecules causes tumors to stick together or separate and metastasize. So in this model, I include cadherins, which are on the membrane of a cell, and they help cells stick together. And then I also talk about integrins and fibronectin, which one is on the outside of a cell and one's in the extracellular matrix. So it helps bind things from the extracellular matrix to the membrane. And I think that's all I've got there. Oh, for this image, it's just one that I found online and wanted to throw it in here. It just shows how different mutations in a tumor can cause that cell line to either die off or proliferate and be kind of the major cell. Okay, so now I'll talk about the significance of modeling these tumors. The first is treatment. So if cancer treatments don't work, they can often make a tumor more proliferative, since the strongest cells will survive and also harder to treat. So basically, we would like to predict the makeup of a tumor so it can be treated effectively. And ideally, treatments in the future can just take data from like a biomarker test and plug it into a model kind of like this and determine the best treatment regime for that type of cancer. And then I also think it's important because studying these adhesion molecules could be relevant in looking at how other molecules come together or break apart. And then for this image that I have here, it kind of talks about why cancer can be so hard to treat. So in picture A up here, the somatic cancer cells are in blue and the stem cancer cells are in red. So if these stem cells metastasize and get away from the main tumor, they can branch off and form other clusters. And then in example B here, the chemotherapy that they use kills everything but the stem cells. So the tumor can come back. And then in example C here, they use anti-stem cell therapy. So it eradicates all the stem cells and the tumor sort of degenerates. Okay, so now I'll take you through some of my approach to modeling this problem. As I mentioned, this model looks at, actually I don't think I mentioned that yet, but this model looks at small tumors and how they proliferate and metastasize. So I started with a 500 by 500 lattice with periodic boundaries on the X and Y. And then for this simulation, there are two different cell types, but they can each take one of three states. So I had to define all of these as separate cell types in the CompuCell model. So for our stem-like cancer cells, which I mentioned last time, we have proliferating, which means they're growing and dividing, quiescent, which means they're just kind of doing their normal job. They're not trying to divide. And then necrotic, which means they're dead. And then same thing for the somatic cancer cells here. Okay, and so the next step that I took in the XML was to use the adhesion flex to incorporate the adhesion molecules that we talked about. And so I had to set up initial concentrations for all these and how they are initially oriented on the cells, on the cell membranes. And then after that, I used the built-in diffusion steppable to define how the glucose moves in the simulation. I used the high diffusion constant with some decay. And it's also important to note that the uptake rates for proliferating cells are higher than for quiescent cells because they're doing more work. And then next, I went into the Python steppables file to denote a lot of the cell behaviors. So selecting which cells will undergo mitosis, checking for health of cells due to glucose starvation, because that's the main thing we look at right now. and then allow for type change due to random mutation and or health. And then it also randomly changes cadherin levels of some of the daughter cells. And so I also initialized one Q stem cell in the center and ran it. So I don't want to bring up my code because that would take too long, but this talks about a lot of the Python logic that I used. So up here in these sort of top two figures, it just talks about if a cell is quiescent or proliferative, if there is enough glucose for them to move on to the next cycle, they will likely do that. So you see here, quiescent moves to proliferative if there's enough health, and then proliferative moves to quiescent once it divides, or if they don't have enough health, they'll die and go to necrotic. And then down here, it talks a little more specifically, the proliferative cancer cells, if they do have enough health to get through, they will always divide and form quiescent cancer cells. And then for the proliferative stem cancer cells here, if they have enough health, most of the time they will go to quiescent stem, or if they do end up mutating, they'll be quiescent cancer cells. So now I'll talk about a few of my results for this. I don't have a lot of results because this simulation took a lot of time to run, even though we are starting with such a small number of cells. So here, as I mentioned, we start off with one quiescent cancer cell, so that's not interesting to model. So after 10 weeks, it grows, and we see a lot of peak cancer cells because this is still a young tumor that's growing fairly quickly. Some of the quiescent cancer cells are mixed in there because they probably have divided recently or are maybe starting to get glucose starved. As you can see, we do have some lower glucose in the middle here. We have a few necrotic cells and then not very many of either type of stem cells here. So yeah, this figure on the right shows the glucose field. You can see that our cell cluster is in here, and within that cell cluster, we start to see a little bit of blue, which means lower glucose, but outside we're still full. And then, so as this runs, the tumor begins to grow, and then due to some of the cells dying and some of the adhesion molecule variables, we see some fragmenting starting to happen here. So still a lot of growth because we see a lot of peak cancer cells, and the middle is becoming a little more glucose starved. So then after 30 weeks, we see almost two distinct clusters now because all the cells here divided and sort of closed in, and they're about the same size, and we're starting to see a lot more or a lot less glucose at the center here. And then in 1 year of simulated time, we see that a lot of these are starting to break down. A lot of the tumor clusters are starting to break down and spread out due to the lack of glucose in the center. So they're all going after more glucose. And so for the analysis of what I've got so far, we see that the tumor is mostly proliferative. There is some death at the center. And then single cells start to break off from the outside, but as the cells die in the middle, it forms two clusters. And then in another run, which I didn't take pictures of, we see that I saw that higher levels of cadherins cause the cells to stay compact for longer. And we also see that glucose is depleted towards the center of clusters. And I haven't got the chance yet, but I want to run it longer to see what happens when the glucose is almost all used up, if the cells will completely break apart or if we'll still see clusters. And then for where I want to go in the next couple weeks, I've been working on introducing growth factors to boost cell death instead of being a limiting factor. I want to help the cells and see what that does. And then I also need to pull the data to create figures for cell count versus time and do parameter scans over those so I can show my data better. It's just been hard. I'm trying to run the simulation so slowly. And then I also want to try out running the simulation starting from a developed tumor rather than a single stem cell. It might be interesting to see how much quicker that will start to break apart. I'm also looking to find the density of each adhesion molecule and note how it relates to the tumor shape at that time. So that'll be kind of another parameter scan type thing. And then I want to find some good parameters that worked and show different biological activities and put those together as sort of suggestion for users who are running this, and then ultimately upload to nanoHUB. And I think that's all.
Great. I mean, one thing that you do run into, which we talked about a little bit, I think Josh talked about in the simulations, is that, as you say, if you start out with a lot of glucose, then the tumor can proliferate a lot before it reaches nutrient limitation. And so the way you source the glucose, what the initial level of glucose is, these kinds of things make a difference to the way this, at least to the initial situation with the tumor. So
probably make it work a little bit faster too, right?
Yeah. But the fact that you're getting different morphologies and some evolution, I think, is interesting. So I think that's good. It's good progress. It's worth. Did you ever? I just sent an email. Did you ever talk to Gilberto or Maciek about this?
No, I didn't get the chance to do that.
Okay, so
focusing more on the paper.
Reminder email. I mean, now that you're this far, I think they could probably have some good ideas to help with how to tune it up.
Yeah.
So you've really got a lot there to work with. How long does that take to run? You said it's slow.
To get the 1 year simulated time, I think it was close to 45 minutes, probably.
Well, simulating a year with short time steps is not.
Yeah.
Take a while, but okay. That's. Okay, good. Any other comments, questions? People are staying right on schedule, so I guess we have. Drew, you're the last today.
Okay. All right, we're sharing. I think we are. All right. So my project is for ovarian cancer tumors and delivering drug routes. So in ovarian cancer, you've got the cancers in the peritoneum, and after through surgery, you remove the macroscopic tumors. You still have to treat the microscopic spheroids with some sort of chemical agent, and that can be delivered either intravenously or intraperitoneally. So this is kind of a comparison. Oh, I've gone too far. It's a comparison between the two methods of delivery, and it also is for the different drugs you may be delivering. And actually want to talk about this slide first. So there's drugs that are small molecule sort of things, and in this project, it's the drug cisplatin, and there's also antibody delivery. And actually, I'm only going to show results for the small molecule right now because I've still got something to work on with the precise values, because it won't really make a difference at the moment. But we also test it for different values of vascularity in the tumors. 0, 2, and 10% for intraperitoneally because it's coming from the outside, and only 2 and 10% for intravenously because that's it. You can't have intravenous delivery with 0% vascularity. And so to start with the model, the first sort of challenge is that I do have to rework, what they've done. I have to make the model myself because they didn't include it in the paper, but they provided a lot of the details from the model that I was able to use. Most values I used for mine, but there were also some questions with some of the data, though. Like in this image that I've provided, it's you can see they've got the simulation with the tumor, and for IP delivery, it looks normal because you see that it's stronger values of the chemical concentration on the outside because that's where it's coming from. But also in the image after that, they're showing IV delivery, and it looks completely blue, which would suggest that there's nothing there. But you can still see that they've got a chart next to it that shows the concentration going up for the molecules per cell. So I don't really know. And the other thing that I was sort of wondering about is why it doesn't just spread all the way up to this. It's almost like it's taking away the chemical, because I would expect this to just be red, but I think, oh yeah, here's some model details. Because our simulation size is just 33 by 33 by 33, and our cells are 1 voxel, and the tumor's 30 cells in diameter, so it fits right in the simulation box. And the cells are also frozen, and they're just taking up the chemical from the outside, and we're measuring that. So for some of the first results, you can see the big sphere of cells that I've got 3D simulation, and I've got a time step that they provided in the paper. They set it to this weird number so that it could just be 1 for the simulation. And you can see it increases and then reaches a sort of equilibrium point up there. But one of my first problems that you could probably tell is I don't have the precise values yet. I think it might be related to a bug with my version of CompuCell. I don't really know. It's I can show it later in the code, but for now, these values are just going to be really relative. That's how I'm comparing these models, but I still come to the same conclusion the paper got. It's just I don't get precise values like they do. And also it happens way too quickly. But yeah, you can also see the sort of just coming in. There's nothing stopping it. So it's just stronger along the outside. And this is for 2% vascularity. I've got a code that I wrote in the Python stepables that makes like lines in random directions until it reaches 2% vascularity. And these cells, as far as the intraperitoneal delivery, it doesn't really, they don't do anything but block the drug coming in. And it reaches a lower number of molecules per cell, and you can see that because it's sort of blocking the drug before it gets to the center. And then there's 10% vascularity in the same way, and it really quickly gets stopped. And so for the intravenous delivery, we do the same thing again, and you can see we already reach a lower number of molecules per cell here because it's not spreading all the way to the outside, depending on the orientation of all the lines that we drew. And then for 10% vascularity, there's a lot more of them, and it reaches a higher value than intraperitoneally. And so the paper came to the conclusion that overall intraperitoneal delivery is better for the general delivery of the drug. And I believe I've come to the same conclusion because I've got a higher maximum average molecules per cell. for most of these, except for 10%. But even for 0% tumors, it would still be higher because intravenous would have a 0 value for that. But also, they did say that having both options used at the same time would provide a better result. But I've got to, I think to finish my model, I want to get whatever sort of, I don't know if it's bugs or if I'm just putting in some values incorrectly, but I've got to fix the time scale and also how much what I'm showing on the plots, because while it works in like a relative way, it's not really reflecting what realistically would happen in real life. I also need to have my model work as I need to implement widgets into my model, because at the moment it's like 4 different simulations that I'm running, and I'm like changing values in the Python and code in XML because I can't control them. But I need, whenever I upload it to nanoHUB, I'm going to need to be able to have it all in one sort of app instead of a bunch of different projects that I'm running together. And that's what I got.
So, I mean, it's dramatic that if you have the peritoneal versus IV source, you get more or less flipped distributions of drug, which is interesting. It's a little disturbing that the published paper has so many obvious errors in the figures. But I think you've done it. It's impressive that you've been able to get around that and actually get some interesting results. Oh, okay, so Yi is on that paper. We should probably add Yi to that. Let me send an email. People should talk. We actually got through this remarkably quickly, so we have time for some discussion if people would like to talk, generally or specifically about the project. Everybody is very quiet. I mean, I hope that when people see each other's presentations, you get a sense of what you could do. I mean, first, what you could suggest for other people to do, and secondly, perhaps what you think you could do to improve your own presentations. I know finding figures and adding diagrams is a lot of work, but these are complicated models, and therefore having those available, I think, is important. Josh, do you have any feedback you want to give right now?
I do not, but I would recommend people trying out. Well, 2 general comments is for those people who are working with intracellular networks. I've talked to some of you independently, but in general, I would suggest getting a good grasp of what the model does by itself, a good understanding of the dynamics of the model are, and what the steady states of the model are supposed to be when taken in isolation. And then to think carefully about what are the parameters that would potentially connect that intracellular network to a multicellular and spatial simulation. That's one thing. And then the other one is, once you've built a model, that also we suggest building step by step instead of just putting everything together at once, is to get a sense of what are the parameters that are being introduced at each step, and how those parameters determine the outcomes of the simulation. Some of those parameters you might have values for from previous work, but for other of those parameters. And in those works, some of those parameters might be experimentally determined, but some of them might be method specific, what we call method specific parameters. And for those, it's important to understand, to do a quick sensitivity and what we call a sensitivity analysis, to understand what the effect of varying those parameters is on the outcomes of the simulation. And using and it doesn't have to be, at this stage, it doesn't have to be anything too complicated. Adding a slider, just as we showed last week, it's enough for you to try different parameter combinations and get an idea of what the sensitivity to those parameters are.
I had one example where I thought that might be useful. For example, Tyler, are you willing to show the slide of your single cell time series?
Yeah, sure.
You have it? That one, yeah. So that would be a good example there. Now the time at which you switch from the increasing IR star to the decreasing one is fixed because you had a switch in the code.
Yeah.
But the value at which the IR star saturates is something that depends on other parameters. I think in particular it was the interleukin-2 concentration. So one thing you could do is run the simulation repeatedly and do the kind of thing we did with the chemotaxis example, where we changed the chemotaxis lambda and measured the velocity. And the same thing in this simulation, you could run the simulation changing the value of IL2, external IL2, IL2CM, and seeing what the maximum concentration of IR star is. And then you'd have a plot where the x-axis was IL2CM, but the y-axis was IR star. And that would give you a sense of what those dependencies is. So that Josh used the term sensitivity analysis, and we didn't really talk formally about what a sensitivity analysis is. But that's exactly what we did. When we said, okay, how fast does the cell move as a function of lambda chemo? How fast does the cell move as a function of cell volume? How fast does the cell move as a function of lambda volume? Each one of those is a sensitivity analysis. You're seeing how a result, the velocity of the cell, changes as you change a parameter with whatever the parameter is. And this would be a good example of that. You could ask the question, if you change the various parameters in your simulation, what changes the time that the cast base takes to turn on, to go from its minimum value to its saturation value? How long does it take? You could measure that and then plot that as a function of the parameters. What determines the maximum level of the cast base? How does that depend on the parameters? How fast does IR star come up? What's the maximum level? How does that depend on the parameters? And so does that, Josh, was that helpful, do you think? I mean, I'm trying to explain the idea of trying to do sensitivity analysis, because I think you're right that it's important. Or for example, in Colley's simulations, you have the oscillations of the cells in their cyclic AMP. What determines the frequency of those oscillations? As you change the parameters in the simulation, the frequency of the oscillation changes. Some parameters have no effect. Some parameters have strong effects. And so you sweep the parameters, measure the frequency, plot those, and then you can get a sense of what you need. That kind of sensitivity analysis may seem tedious to do, but when there's a problem, for example, all your cells here are dying before they're differentiating. Or in Kali's case, you're not getting the set of cells that need to move in a particular way. If you know what the dependence of the key behaviors is on the parameters, then you have a better sense of either where there's a bug, if there's a bug, or what parameter needs to be changed. Another one you could do for, say, Kali's case would be you get traveling waves if you have the cells in a continuous sheet. What determines the frequency and wavelength of the oscillations? So you can run that simulation again and again and again, changing parameters, plotting wavelength and period or frequency versus wavelength and frequency versus, I don't know, the rate of secretion of cyclic AMP, the uptake or the diffusion constant of cyclic AMP, and so on. That's typically how people actually, they don't always show those results when they publish their papers, but they almost certainly did that kind of work when they were developing their models. And so that's something to think about especially when you're stuck. If the paper didn't publish all of the details. It's sort of disappointing in a way to say that these papers don't publish enough information to replicate them in a clean way. And I'm not being critical of any of you for those issues, but part of the learning experience is to try to do this. I mean, principal science is supposed to be, as Kali had that very humorous picture, science is supposed to be reproducible. And with an experiment, you can always blame it on some detail of the experiment. With computation, it's a little harder to blame non-reproducibility on the computer. And so I think that's something to think about. Josh, did you have any more you wanted to add to that?
No, I think you covered it all.
Again, I mean, please do take seriously the idea of helping each other. I mean, for example, Devin and Drew, you're both working on cancer simulations. And so now that you've seen each other's work, maybe you could talk to each other a little bit and leverage a little bit off of that. Tyler and Kali are both doing simulations with cell motility, which cell motility and chemotaxis are very important, where you have relatively complicated intracellular models. So possibly there's some overlap there. I know, I mean, Jeffrey and Fanbo and Andy are working together sort of separately because of what they're doing for Mechanica, so it's a little bit different. But I think, I hope now that people have made a lot of progress. There's still going to be some work getting this finished. But I hope going through a review like this was useful. So the plan is, I'd like to try to meet with people one-on-one before next week. Critically, everybody should meet one-on-one with somebody, whether it's me, TJ, or Josh, and go over things. Please talk to each other. And then we're going to do this again and potentially again. You don't necessarily have to repeat everything you did this week, next week. But I would like for next week to have everyone have critiques for each other so that you looked at each other's work and you can help each other out so that we can make these things as useful as possible. Any questions before we break? It'll be the first day of the semester. We end early. Any comments? No. I know people are probably tired at this stage of the semester. People are probably tired. Glad to have a little bit of extra daylight. Well, I encourage you, go out. It's a beautiful day. Go out for a walk. Enjoy the sun while you can. It's nice that it's still light at the end of class. And I want to thank everybody for the work you're doing. And I want to work with you to make sure that these projects are really things that you can be proud of. You could already be proud of what you've done, but I want them to be up on nanoHUB and things that people are proud of, so that when people reference them, it's something that you want to show off. Okay, thank you, everybody. I'll be talking to you one-on-one, and please do try to do comments for your classmates so that we can all work together to make this work. And with that, I'll say good night. Thanks.
Thank you.
Bye.